Hello, everyone. My name is Ding. I'm a PhD candidate at George Mason University. Our work is innovating multi-user volumetric video streaming through cross-layer design. It is a joint work with Dr. Bo Han, Dr. Pars Patak, and Dr. Haoliang Wang. Let's start with what is volumetric videos. A volumetric video is a new form of video. The viewer can explore the 3D content in 6 degrees of freedom, including 3 degrees of position and another 3 degrees of orientation. It can provide a highly immersive experience for users because users can change their viewports like they are viewing real things. Here is a demo showing a user wearing a VR headset and watching a volumetric video. The volumetric video can enable lots of new virtual reality and augmented reality applications in education, entertainment, and remote healthcare. Well, volumetric videos have been explored for a single user in past work, but there are many applications that require multi-user volumetric video streaming. For example, multiple designers collaborate to design a building, or teachers show scientific demos for many students. And the reason why the multi-user volumetric video streaming is not explored is that it is extremely bandwidth intensive even for a single user. In the volumetric video, each frame is represented as a point cloud, where each point includes coordinates and color features. If we use 2 bytes for each coordinate and 1 byte for RGB respectively, we need 9 bytes to store a single point. Now, let's take the widely used ATI point cloud dataset as an example to check the bandwidth requirement for the single user. To support 550K points per frame, it requires 1.18 gigabps data rate. And if we use the Google Draco library to compress the data, it can further reduce the bandwidth requirement to 364 megabps. In our previous work, Vivo, it applied 3 optimizations, including distance, viewport, and occlusion optimization. The required bandwidth could be further reduced to 232 megabps. But our question is that whether it is good enough for multiple users. To investigate this multi-user problem, we did a measurement study to run the optimized streaming system on the current 802.11ac WLAN. Here, we show the frame rate when scaling the system to multiple users. And we can see that to support 30 frames per second frame rate, the current WLAN cannot even support 2 users with good quality in the optimized system, let alone using the higher points density. So, to provide the higher bandwidth to support multiple users, we ask this question: whether we can use gigabps mmWave WLAN to stream volumetric videos to multiple users. To answer this question, we repeated the measurement study of streaming the same volumetric videos in 802.11ad mmWave WLAN. And we found that mmWave WLAN is feasible to support up to 4 users. However, we also observed the well-known mobility and blockage problems in mmWave WLAN. Motivated by these observations, our goal is to build a multi-user volumetric video streaming system in mmWave WLAN. But we need to solve 2 fundamental challenges. The first challenge is how to mitigate blockage and mobility-related problems in mmWave WLAN to improve the frame rate. And we propose to use multi-user viewport prediction to predict the blockage events and proactively react it with a cross-layer solution. The second challenge is how to reduce the bandwidth requirement and improve the video quality or increase the number of the users in our system. So we proposed to use multicast transmission to transmit the overlapped content between the user's viewports to further reduce the bandwidth requirement. So the first challenge we consider is to mitigate the blockage and the mobility problems in mmWave WLAN. In mmWave WLAN, APs need to use a phased array to concentrate their signal to users. When users move, APs need to track the user and point the beam to the new position of the user. In addition, in multi-user scenario, one user can block the beam of another user and even breaks the link. As shown in this figure, the throughput significantly drops because of this blockage event. To solve this blockage and the mobility problem, we propose to use the 6DOF viewport prediction information from the application layer. In viewport adapted volumetric video streaming, users need to predict the 6DOF information for a short interval. So we can utilize this prediction process to predict the location and orientation of users to infer mobility and blockage events in mmWave WLAN. For instance, at time t1, user 1 and user 2 have their predicted traces for the next couple of frames. Well, in the AP's point of view, it can infer that at time t2, user 2 will block user 1 in line offset. So by predicting this blockage event, we can then proactively prefetch more frames in the user 1's buffer or switch the beam to go across the blockage to prevent the video stop. The second challenge in our system is how to further reduce the bandwidth requirement. And our solution is to multicast the overlapped video content among users. As the very first step, we investigated whether and how the users' viewports are overlapped in multi-user scenarios. We used the traces collected in a previous study where 32 users were asked to watch a few volumetric videos, and their 6DOF information was recorded for each frame. We define the viewport-similarity as the intersection over union of cells within the user's viewport at each frame. And take this soldier frame as an example. We first partition the point cloud into different cells. We then calculate the viewports of each user with frustum calling based on their 6DOF information. Then we calculate the viewport similarity as the intersection over union between these two viewports. Here, we draw the CDF of viewport similarity among all studied users with different partition sizes and the number of the users in the group on this red figure. We can see that there is a significant overlap content between users. It provides us with a high potential to reduce the bandwidth requirement. So now the next question is how to do the multicast with this high content similarity. The challenge here in mmWave WLAN is that to cover multiple users with different positions is not easy because the default beams used in the AP's codebook are for single users, and they are not designed to point to multiple directions. And we conducted another measurement study to measure the supported multicast rate when the access point used the default beams. And we found that the default beams with one single lobe cannot support efficient multicast for multiple users. So to tackle this problem, we design multi-lobe beams by adding multiple antenna weights together and weighted by the received SNR. This second figure shows the two customized mean lobes pointing to two users in our system. We then simulate the potential improvement of multi-lobes in a commercial mmWave channel simulator RAMCOM. And the results shows that the multicast with multi-lobe beams in our system can improve the throughput effectively. And here are some open challenges, and we hope that they can inspire some discussion and new ideas in our community. The first one is multi-user viewport prediction. Though we can currently predict the user's viewport individually, there are interactions between users when they are watching the volumetric video, which will affect the prediction results. So a joint multi-user viewport prediction model is needed. Secondly, building mmWave multicast with multi-lobe beams is challenging in commercial devices because of the limited phase and amplitude resolution in the commercial phased array. Thirdly, to adapt the video rate, we need an accurate bandwidth estimation. Here, we can utilize the mmWave WLAN throughput estimation to improve the traditional video rate estimation. Lastly, to further increase the number of the users, we can include multiple APs. To this end, we need a good interference management scheme in mmWave, and the control overhead is another problem when involving multiple APs. So this is the end of my presentation. Thanks for watching. We are happy to take any questions. Thank you.